All right, everybody, buckle up, because today we are diving deep, and I mean deep, into the world of self-referential paradoxes.
Sounds fun. Are we talking about those classic brain teasers like, this statement is false?
Exactly. You guys send in some awesome excerpts from this paper by Noson S. Yanofsky. It's called A Universal Approach to Self-Referential Paradoxes, Incompleteness, and Fixed Points.
Catchy title.
Right. And it's not just about those fun little logic puzzles. This paper actually connects them to some really complex ideas in computer science, even like the foundations of mathematics.
Okay, now you've got my attention. So we're going beyond just playing with words. We're talking about the limits of logic itself.
Yeah, it's like these paradoxes are hinting at something fundamental about how we build systems of knowledge, about the very nature of information itself.
Okay, I'm ready to dive in.
Fantastic.
What's Yanofsky's main argument here?
Well, he starts by saying that these paradoxes, they're not really logical breakdowns.
Wait, what? But they lead to contradictions, right?
They do, but Yanofsky says they're more like cracks in the foundation of our formal systems, like the blueprint we're using to build these systems has some inherent flaws.
Interesting. So it's not that logic itself is broken, but the way we try to systematize it is inherently limited.
Exactly. And to understand these limitations, he takes us on this journey that starts with a concept from set theory. You familiar with Cantor's theorem?
Vaguely. Something to do with sets and infinity, right?
Right. Like imagine you have a basket of, say, fruit. Cantor's theorem basically says that there are always more ways to group that fruit than there are pieces of fruit.
Okay, that makes sense. If I have an apple and an orange, I can have a group with just the apple, just the orange, both, or neither.
Exactly. And that's fine for a small example, but this gets really wild when you start talking about infinite sets, like the set of all natural numbers.
Okay, I can see how that would get really mind-bending really fast.
Yeah.
So how does Yanofsky connect this to paradoxes?
Well, he says that this idea, this relationship between a set and all its possible subsets, it can actually be generalized to understand limitations in other systems, not just sets.
Oh, okay. So we're not just talking about apples and oranges anymore. We're talking about the nature of language, of computation, even of knowledge itself.
Exactly. And he illustrates this by diving into a whole bunch of famous paradoxes, like Russell's paradox. You know that one.
Yeah, that's the one with the set that contains all sets that don't contain themselves, right? It's like a logical pretzel.
And that pretzel shape, that contradiction, is exactly the point. Yanofsky shows how this seemingly simple paradox actually reveals a flaw in how we think about sets.
So it's not just a fun brain teaser, it's a sign that even our most basic logical tools have limits.
Exactly. It's like we're trying to build this perfect airtight system of logic, but there are these tiny cracks, these fundamental limitations that keep popping up.
So how do we deal with these cracks? Do we just have to accept that our systems will always be incomplete?
That's a great question, and it's something we'll explore more in a bit. But first, Yanofsky takes us even deeper into this world of paradoxes. He talks about Grelling's paradox, the liar paradox, even connects these ideas to computer science with things like Turing's halting problem.
Okay, I'm gonna have to refresh my memory on that one. Turing's halting problem, that rings a bell, but...
It's basically the idea that you can't create a program that can tell you if any other program will eventually stop running or just keep going forever.
So it's like trying to predict the future of every computer program ever written.
Exactly. It's this concept that shows how even with something as powerful as computers, there's still fundamental limits to what we can know.
This is already making my head spin. I'm ready for a deep dive into some of these specific examples. All right, so we've been exploring all these paradoxes, these like little cracks in the foundation of logic. But what about the flip side? What happens when self-reference doesn't lead to a contradiction? That's where things get really interesting. Yanofsky introduces us to something called the diagonal theorem, and it's like the yang to Cantor's theorem's yin.
Okay, so if these paradoxes are like warning signs, is the diagonal theorem showing us a safe path forward?
In a way, yes. While Cantor's theorem highlights the impossible, the diagonal theorem explores what's possible when a system can consistently refer to itself.
So it's about finding those special cases where self-reference actually works.
Exactly. It's about finding those fixed points where the whole system doesn't implode on itself. Like, think about Gödel's incompleteness theorems. They show us the limits of formal systems, but they also rely on the existence of these fixed points.
Wait, so the very thing that shows us the limits also points to a way for the system to work. It's like saying a map can never be perfectly accurate, but there are specific points where it lines up perfectly with the real world.
Exactly. And the diagonal theorem helps us understand how those points of perfect alignment can exist.
Okay, my brain needs a minute to catch up, but give me an example. How does this diagonal theorem actually work?
Imagine a map of a city, right? And on that map, there's a tiny map of the same city. And on that tiny map, there's an even tinier map, and so on, forever. The diagonal theorem is like finding that one specific point, maybe a building or a street corner, that shows up in exactly the same spot on every single map, no matter how small.
Whoa. That's trippy, but I think I get it. So even though the map as a whole can't be completely accurate, there are these points of perfect self-consistency.
Precisely. It's like saying if we could have a perfectly accurate and complete system, those fixed points must exist.
So it's not just a mathematical curiosity. These fixed points have real implications, right? Like in computer science, with something called the recursion theorem.
Absolutely. The recursion theorem is like magic in the world of computer programs.
Okay, how so?
It basically says that any program can be made to output its own source code.
Wait, hold on. So like a program could print out a copy of itself.
You got it. And that might sound simple, but it has huge implications for things like compilers, which are programs that translate code from one language to another. It even has implications for artificial intelligence.
Because if a program can modify itself, it can learn and evolve.
You're getting it. This idea of self-replication is at the heart of the recursion theorem.
Okay, that's both incredibly cool and a little terrifying.
Right. But there's more. Remember we talked about Rice's theorem, the one that says we can't write a program to figure out every property of another program?
Yeah, it's like trying to program a computer to judge a beauty contest. Some things are just too subjective.
Yeah,
Yeah.
exactly. And the recursion theorem helps prove that Rice's theorem is true.
Whoa. Okay. How does that work?
Well, imagine you could write a program that could tell you any property of any other program. The recursion theorem lets you use that program to create a contradiction. It would be like the program saying, I can analyze any program, including myself, but I can't analyze myself.
So it creates this logical loop that just breaks the whole system. Man, every time I think I'm starting to understand this stuff, it's like another layer gets peeled back. It's kind of humbling.
It really is, but it's also exciting. It means there's always more to explore, more to learn, and that's what makes these paradoxes and theorems so fascinating. They challenge us to think differently about the nature of knowledge, about the limits of what we can know, and even what it means to know something in the first place.
It's like we're trying to catch lightning in a bottle, but the very act of trying to grasp it changes its nature.
I like that analogy. It captures the essence of why these concepts are so slippery, so elusive.
Okay, so we've gone from ancient paradoxes to self-replicating code and even touched on the foundations of mathematics. Where do we even go from here? Okay, so we've gone pretty deep down this rabbit hole of paradoxes and theorems, but I have to ask, what does it all mean for, like, the average person? We're not all mathematicians or computer scientists, but this stuff still feels important. How does it connect back to our everyday lives?
You're right, it's not just about abstract concepts. I think the real takeaway from Yanofsky's work is that every system we create, whether it's a system of language or math or even just our own way of thinking about the world, it comes with these built-in limitations.
So no matter how hard we try, there are always going to be these blind spots, these things we just can't quite wrap our heads around.
In a way, yes. But I think there's something liberating about acknowledging that.
Liberating. How so?
Well, it allows us to approach these systems with a bit more humility, Instead of getting caught up in trying to find the one right answer, we can embrace the ambiguity, the mystery.
That's a good point. It's like instead of seeing these limitations as roadblocks, we can see them as opportunities for exploration, for asking new and more interesting questions. Which reminds me, Yanofsky ends his paper by pointing out some areas where his framework could be applied, but hasn't been fully explored yet. It's like he's throwing down the gauntlet for future researchers.
Oh, absolutely. He mentions some real head-scratchers, like the Berry paradox, which tries to define a number based on how hard it is to describe. It's another one of those self-contradictory loops. And then there's the crocodile dilemma, which is just a fun way of illustrating how tricky self-referential logic can be.
Right. It's like we're constantly bumping up against these boundaries of what we can know and how we can know it. But maybe that's the whole point. Maybe the pursuit of knowledge is more about the journey than reaching some final destination.
I love that way of looking at it. It's not about having all the answers, but about appreciating the mystery, the complexity. And that's what makes these deep dives so rewarding. We might not come out with a neat and tidy solution, but we come out with a deeper understanding of the questions themselves.
Exactly. So to all our listeners out there, as we wrap up this deep dive into the world of self-referential paradoxes, here's something to ponder. If these limitations are baked into any system we can create, what does that say about the nature of knowledge itself? Are there some truths about the universe that will always remain just beyond our grasp? Or is it that very pursuit, that constant striving to understand, that truly defines what it means to be human? Keep those questions simmering, and we'll see you next time on A Deep Dive.